Hi everyone, this is Mr. here, and this video we're going to be looking at percent composition and how we can determine the actual formula or molecular formula of a compound from the percent composition. So I thought I'd start by reviewing what percent composition is. So when you're doing percent composition, you have to remember you're comparing the mass of each individual element here to the mass of the entire compound. So what you do is this. We'll use an example here. You need to determine the molar mass of the whole entity. So for example, if I've got formaldehyde here, CH2O, I'm going to determine the mass of the entire molecule in this case. So it's going to be 30.03 grams per mole. And we're going to be doing this. We're going to be comparing the mass of 1 mole of each of these elements, carbon, hydrogen, oxygen, to the mass of the entire compound. So when you do that, all you do, again, is you take the mass of the element over mass of the compound. So here I've got carbon, and you take the mass of the carbon, 12.01, divided by the mass of the entire formaldehyde molecule, and you end up with 39.99%. You do the same for each of the other elements. For hydrogen, getting 6.72%, and finally for oxygen, we've got 53.28%. So now that we've done that, let's look at this. So what I have here, I've got formaldehyde. We just determined the percent composition for formaldehyde. How about acetic acid? Now, we looked at this the other day. Acetic acid has the same proportion of each of the elements. So formaldehyde has 1 carbon for every 2 hydrogens for every 1 oxygen. Well, acetic acid has 2 carbons to 4 hydrogens to 2 oxygens, but we can reduce this to 1 carbon, 2 hydrogens, and 1 oxygen. It has the same proportion of each element as formaldehyde. So when we determine the percent composition for acetic acid, it ends up being exactly the same. It has the same percentage carbon, same percentage hydrogen and oxygen within the molecule as formaldehyde. Now, the reason is because both of these, even though they have a different molecular formula, they have the same empirical formula. Remember, the empirical formula is the ratio of each element in here. So what we're going to now do is we're going to go backwards. We're going to use our percent composition to determine the mass of the element, of each element. Then we'll determine how many moles of each element are present, and then we're going to figure out our empirical formula. So we're going to start over here. So in this case, I have a substance and it has 27.3% carbon, 72.7% oxygen. We don't know the mass. So if we don't know the mass, we assume that we have 100 grams. It makes life a little bit easier for us. So I know that if I've got 27.3% carbon, if my sample was 100 grams, I'd have 27.3 grams of carbon in that. Same thing with oxygen, 72.7% would mean 72.7 grams in a 100-gram sample. Now we've got our mass. Next thing we have to do, we're going to figure out how many moles we have of each element. So to do that, all you do is you take the mass of each element and you divide it by the molar mass of the element. So here we have 27.3 grams of carbon. We divide it by the molar mass of carbon, 12.01. So we'd have 2.273 moles of carbon in my 100-gram sample. I do the same thing for oxygen, and you get the number of moles of oxygen. So where are we in my checklist? I'm over here. Now I need to get a formula. So to get the formula, all you have to do is determine the proportion of in terms of moles for each of these elements. So all I do is I'm going to be comparing the amount of carbon to the amount of oxygen. And the way you do that, you set up a little ratio. So I've got 2.273 moles of carbon for every 4.544 moles of oxygen. So that's an odd number. I want to make it a little bit easier. So I'm going to divide both sides by the lowest value, which is 2.273. And when we do this, on this side, I end up with 1. And on this side, when we do a little bit of math here, we end up with 2. So that means that for every 1 carbon, I have 2 oxygens. Now, what do we do next? Well, simple. We write this as a formula. So if I write this as a formula, it's going to be CO2. So again, 1 carbon for every 2 oxygens. But you have to remember this though. this is my percentage in my empirical formula, my proportion. So I don't know what my real formula could be. It could be CO2, C2O4, C3O6. All of these are possible. All of these have one carbon for every two oxygen. So the next example, we're going to be looking at how we can determine the real formula or the molecular formula for a compound. So to do that, what we're going to be doing is we're going to be using a little flow chart up here. So it's the same flow chart. So first thing we're going to do, we'll determine the mass of each element in the sample. This is from the percentage and the mass of the sample. Then we're going to figure out the number of moles of each element from the molar mass, just like we did before. And then we're going to use our molar ratio to figure out the empirical formula. And then we're going to do something that's we're going to find out the X, and the X is going to help us figure out the actual molecular formula. So we're going to go through an example here. So let's look at this sample here. So what I have here is I've got a sample and it has 25.9% nitrogen in it, 74.1% oxygen. I don't have a mass of the sample. All I know is the molar mass. This would be the mass of 1 mole, but I don't know how many moles I have. So we're going to here assume 100 grams. So we always do that. So we're going to do this little assumption here. So when we assume 100 grams, you have 25.9% nitrogen, and we have 100 grams. So in the 100 gram sample, 25.9 grams will be nitrogen. Now for the oxygen, we're going to have 0.741 or 74.1% in the 100 gram sample. So in that sample, we're going to have 74.1 grams of oxygen. So even though it's kind of obvious, you want to make sure you actually write down this little statement somewhere so you know exactly what you're dealing with. Next thing we have to do is we have to figure out the number of moles. So what I know is I've got 25.9 grams of nitrogen, and I know that 1 mole of nitrogen has a mass of 14.01 grams. And I do a little bit of math over here. And what happens is we end up with, let me see here, 1.8487 moles of nitrogen. I'm not going to do very much rounding right now. I'm going to leave this as lots of extra decimal places. Then we're going to do the same thing over here for the oxygen. So we've got 74.1 grams of oxygen, and 1 mole of oxygen would have 16.00 grams. So do the same thing over here. And we find here that we're going to have 4.63125 moles of oxygen. So now what we have to do is we know the number of moles. We have to use our molar ratio to figure out the empirical formula. So what I know is this. I've got 1.8487 moles of nitrogen to 4.63125 moles of oxygen. So I need to do a simpler ratio, so divide both sides by 1.8487. And when we do this, what happens is this side becomes 1, so we have 1 nitrogen. And over here, we're going to end up with, looks like 2.5 oxygens. So every 1 nitrogen has 2.5 oxygens. That's an awkward number. When you have whole numbers, so the easiest thing to do would be to multiply both sides by 2. So every 2 nitrogens, you're going to have 5 oxygens. So what would my formula be? So my empirical formula would be N2O5. But remember, I don't know the actual formula. it could also be N4O10 as long as there's 2 nitrogens for every 5 oxygens, as long as that ratio is true. So this is where the molar mass comes into play. So I'm going to figure out the molar mass of the empirical formula. So the mass of this is going to be, so the mass of the empirical formula, whatever we have here, I'm going to have 2 nitrogens. Each one is 14.1, so it's going to be 28.02 grams just for the nitrogen. And then for the oxygen, I've got 5. Each one is 16, so it gives me 80.00 grams. So the mass of this, molar mass, would be 108.02 grams per mole. So in 1 mole, I would have 108.02 grams. Now, this would be the mass of this ratio. Now, when you look up here, the mass of the actual compound is 216 grams per mole. So here's what we do. We compare the real mass, this would be the molecular formula mass, which is 216 grams per mole. And we compare that to the mass of this empirical formula, which is 108.02 grams per mole. And you end up with 2. So what that means is that my molecular formula is twice as big as my empirical formula. So that means that I've got to take this formula, N2O5, and multiply everything by 2. So I'm going to have N4O, so it should be a 5, 10. So N4O10 is my actual molecular formula. So again, what we did is up here, looking at the percent composition, we knew the percentage. We figured out the mass, assuming 100 grams of the sample. Then we did the number, determined the number of moles over here, and used the molar ratio to figure out the empirical formula, which was N2O5. Then I had to figure out how much I had to multiply the empirical formula by to get my molecular formula. So we compared the mass of the empirical formula to the mass of the actual compound, the molecular formula. We found the molecular formula is twice as big. So we need to have twice as many of all these atoms. So our formula, N4O10. So that's it. So you have to practice. There's lots of examples that you can actually do on the workbook pages. Have some fun with them. But you do need to practice though.